be
I
paying
like
you.
Ross. I probably have one motor. I like Ross's two though.
I don't know if I can do 8 miles in a week, so.
Yeah, let's go.
Why would I make myself do it?
It's fun. It's good. It's healthy. Okay. Okay, one thing. Let me give you guys your back first.
You know what they just turned in?
What?
You know what they just turned in?
Yeah, well, I can't give that back to you. In fact, now I need to hold on to everyone's for that one. It's fine.
That's it. That's one for 25.
What? That was the one you turned in Friday, or that you just turned in right now. So the way this works, I decided I'm going to curve all homeworks. So whoever gets the highest, that is the new curve. So on your first assignment, yes, the first assignment, the curve was 4 1/4.
What do you mean?
And the second assignment, the high was 5. So, in other words, homework was out of 5 for the second one, and 4 1/4 for the first one. Did I give somebody Brad's? I'm missing Brad's
So,
understanding.
so 5 out of 5 is good.
Yeah. 5 out of 5 is good, yes. In what class is 5 out of 5 bad?
I don't know. In relative physics, I don't know.
Okay.
You kind of hurt my hands broken for all I know.
I'll put up and fill back in when I change.
When was this?
Oh, I just, I
What the
forgot.
crap is all this?
I,
That's fine. And
I
you just
forgot.
magically made that go away.
Yeah.
That was convenient. Just, I don't know when to do this. Poof, it's gone.
I was hoping you wouldn't notice that.
Yeah, it just disappears. I'm sure there's other space I didn't notice, but I didn't notice.
I'm pretty sure that's the only one I
Okay. My eagle eye. Yeah. Alright, so on to next topic.
The reason why that word because I'm stupid and leaving a space.
Oh. Okay. Well, just if you need to do each problem on a different page or something. Okay, your exam. Your exam's going to be on Thursday. We're going to be able to finish up chapter 2 today. It'll be a small reading assignment, but nothing computational.
Next
so basically,
Thursday?
No, it's Thursday.
This Thursday?
No, but everything that you guys have already learned, we're not learning anything new today. We're just going to finish that example problem and your homework that you already have that was supposed to be due today, and that'll be now due on Thursday. We'll cover the last topic that we need.
You want to do the exam like Tuesday?
If you guys really want to push me to do that, we can jump into chapter 3 on Thursday and have an exam instead on next Tuesday.
Wait, so you're saying the thing's this Thursday?
Yes. That was my hope. Is that a huge problem? I mean, that was originally what we talked about last week, but then, of course, that was...
We assume everything's getting moved.
No, I understand. I was still hoping to have it on Thursday. I can be persuaded if it's a large problem. Yes, true.
Would you be willing to maybe mention some of the things we should focus on?
Yeah, we can even talk about that. It's an in-class exam, so it can't be that bad. And I'll even tell you the things that I'm looking for. What do you got?
they give us that one exam that he gave us.
I can do that. I can post that on
I just have a solution to
the solution guide for that exam. I don't know if I have one. I can do that. I can try and get that together.
Well, if it don't matter between, if we're going to do the same thing on Tuesday, we're going to do it on Thursday, just give us 4 more days. That's fine.
I'd rather Tuesday because I have tests. I can plan to see Sims for the next 2 days.
Okay. What's your best?
I'll go with Tuesday.
I use the holes card and go for Tuesday.
Just do the vote for Tuesday. All right, then we'll do that Tuesday.
Trying to be persuasive.
Which I guess that's fine because then I get your homework back for you guys. The one that you just, yeah, I'll get your 2 homework assignments. That way you can turn your homework assignment in. They'll still be due Thursday, and I'll get that back to you by Friday somehow. In a way that kind of makes my life easier. My next 2 days are very busy, very very busy.
You see, it works out for all of us.
Sorry. But that means Thursday we're going to jump into chapter 3 and stuff that won't be covered. So we got to, we're not behind per se, because I think this first section will take a while, but to be ready in week 7 without a test is kind of long. So.
Also, I'm gonna work that like 2 hours away though.
And what?
I'm gonna work it out. I'll tell you later.
Okay, so let's finish up today. We might even be able to talk about the exam a little bit at the end. All right, so where we ended up last time, we were talking about this general relativity concept. Okay, so here's a person who said that a light flash goes off and they see it sometime later. The distance between here and here, so the distance of h. And we say that this spacecraft is accelerating with the same gravity as Earth. Okay. Now, Newton's idea, his principle, was that this had to be identical. Newton's principle, he argued that this has got to be the same as being on Earth. Okay, seeing the light come up here, because here we've got the acceleration of gravity pulling us down. Now this seems weird that we would have to go up that direction, but gravity is pulling us down in this way. But if you think about it, the spacecraft was going up, accelerating the G. It'd be the equivalent of you feeling that you were pulled down onto the ladder. Okay, and this is the same exact situation where there's gravitational field. Now we came up with this and said, okay, now if you were to run any experiments with this spacecraft off in the middle of nowhere, as far as we can tell, and that there should be no difference. There's nothing in Newton's laws, anything that should tell us that there's any difference between these two scenarios. So let's create an experiment that might show that there is a difference. So if a flash of light goes off here, we know that a light is always going to travel at c, speed of light. So we know what reference frame it's in. Off it goes. All right. So the amount of time it takes for the light to get here to here, we can say the change of t is going to be equal to h over c. Okay, the amount of time it's going to take the light to get here. Now, the problem is, once the light gets here, we are now moving away. So we actually can erase that. And you can put a motion in your cap or something. Like this up. So now we have some sort of velocity in this direction. And the velocity is going to be equal to the acceleration times the time. That is now the velocity that we are moving. So we are moving away from this object. So we're going to see the light as redshifted. Okay, we're going to see that the wavelengths actually increased. Now the weird thing about this might be, I want to talk about a few things that at least came to my mind. They might have concerned you as well. When the light went off from here, we're saying that it's traveling at c, but the light source, everything is moving with us. So wouldn't this just be a reference frame that's moving along? Yeah, what do you got, Drew?
I was going to say, would it maybe not be just because, I don't know, the source of the light is moving with respect to the reference frame?
It's moving with it, you're saying?
Yeah.
Well, now that's the question. Now, if the light source is moving with zero velocity with respect to the reference frame, so this whole thing is going up, then it doesn't make any sense that we would see a redshift, right?
So is it not somehow?
It's
Does
not.
gravity not have to be the same at reference, right?
Say again?
Does the force of gravity not have to be the same at reference?
No, we're going to assume that it is in the sense that acceleration is always moving up at all times. Now, but what's going on here is this is not a constant velocity problem that we're dealing with. This is an accelerated velocity problem. Here, when the light went off, we were at speed zero. We're going to assume there was zero velocity. Then we started to accelerate away. By the time the light got to us, we were now moving with the velocity. Okay. Now, let me try and explain this in another way, so we can think about it being redshifted. Let's think about it driving away. So Kyle and I are standing here, and we're playing catch. He throws me the ball, I throw it back to him. Okay. Now let's take this and say you had a ball shooter instead. So you're shooting at a ball at me 1 per second. They're hitting me, okay? Now what happens if I start to accelerate away? If I start to accelerate away, if I'm moving faster like this, one ball is going to hit me, and the next one's going to take a longer amount of time to hit me because I now have a greater velocity. Every single time that happens, the balls are taking longer and longer to get to me, even though they're launching at the same rate there. Eventually, you could get to such a speed that you're outrunning the balls, and none of them get to you. Does that kind of make sense? What do you got, Drew?
So in this problem, the rocket one, not the thing you were talking about, well, every time the light goes off, H is always the same, but the gain velocity, you know, from when the light goes off and when it gets to us, our velocity has changed in between those times.
In between that small amount of time.
So even though it's H, you know, we're still moving, so it's taking light longer, to get to us. So.
Right. Now the idea being here, so we're going to talk about this. Now we're up here, so there's this height change right here. So technically, the distance, we would say that this is approximately the change in times h over c, because technically we've gone an extra little distance. Now, the other assumption we have is that b is very small compared to the speed of light. So this spacecraft is not, it's not flying away from here, it's not moving very quickly. Okay, so that distance is small. H is much larger than this change in distance here. So that's why we just approximated it as delta t. We could put another term in here, but it would factor out, or not factor out, but it would be increasingly tiny here. All right, so because that distance is so small, and we're assuming that light is only traveling a distance h, and the velocity is much, much smaller than c, we were able to reduce our Doppler shift equation to say that 1 minus v over c times f source is going to be our observed frequency. Okay? And this is the one I think you actually use in your homework as well. It simplifies when the velocity is much lower than c, binomial approximation. All right, so our velocity, as we're going up here, we're going to say velocity is equal to at, which is the same thing as saying acceleration equals the change in velocity over t. So if that's true, velocity equals at, and t is equal to hc over here. A, we already said, is equal to our gravity. We're going to try to accelerate with that. So we can say that this is going to be gh over c. We now have a term for what our velocity is. As such, we can actually throw this directly in here and figure out what our observed frequency is from our source frequency. Just plug in gh over c. So now, so when Einstein postulated this, he came up with this idea that said that this is the same situation as this. So there's two cases that we can deal with. Either A, he's right, or B, we found the very first experiment that shows that there's not the case. Because if we're seeing a red light shift here, then the question is, will we see the red light shift here? Okay, and there was no way to really determine this at the time. But let's put some numbers to it. All right, so we talked about this last time. We talked about 600 nanometer light, okay, which is what color? Orange. Yeah, so it's not quite red. Red is around 700. So 600 nanometer orange light. All right, that has a frequency of 5 times 10 to the 14 hertz. That's our frequency. This is our wave. All right, that means, let's look at Bob. Bob is, how are we going to do this? Okay, we'll call this Bobcat. Cute. So Bob's up there, and he's watching this. He watches for 1 second. In theory, 5 times 10 to the 14 wavefronts would appear to him in 1 second. But since he's moving away with an accelerated velocity, that won't happen. This gets back to the idea that I was wanting to talk about with the driving, where if Kyle's shooting baseballs at me. Does that kind of make sense, that example that I was giving? Even though all of those balls are still in the air, they're not getting to me. That's actually an interesting way to think about relativity in general, because now let's think about those balls being photons, light. So what is the only way that I can outrun the light then to get to the point that I'm not seeing any wavefronts, and that's I would have to move the speed of light myself. Okay? Otherwise, the light is just going to look like it's shifted. They're just going to be getting to me slower as I'm accelerating. Okay? Okay. All right. Now, what happens when they get to a constant velocity, though? Will they continue to look further apart or no?
Look the same.
They look the same as when he's launching?
No. But get constant then.
They would get to a constant rate, right? It wouldn't be continually redshifted, but it would still be redshifted because the balls are moving along. So you can think about this as like 2 cars. So the balls are moving along like this. So they're coming along as you're watching, but I'm driving along like this. So one would hit, and then the next one would hit, and then the next one would hit. It's playing the catch-up game, okay? So it would be very delayed. And the reason being is that, yes, all the balls are still being launched there, but the distance between him and I is becoming larger, so more of them can fit in that space. Okay. Okay, so the point being is that for Bob to see all 5 times 10 to the hertz wavefronts, he has to wait a longer amount of time in the spaceship, a slightly longer amount of time. So he says, now let's look at this a different way. This guy says a second went by, and I sent a second of light to you. Bob says, no, it took me 1.1 seconds to see that. Okay. So from his point of view, it's looking like the time is actually changing, and it's by the exact same factor. So this is what we talked about before. Time lower is going to be equal to change in time higher, 1 minus GH over C squared. This is the exact same term that we have over here with the GHC and for our frequency observed versus source. So for the lower time, we're going to find that this happens in less time than the higher. So if we get a certain amount of higher, so say that this is, 1 second up here, and this is going to be 0.99 seconds, or maybe I'll go through the same example in just a second. So let's say for lower, we said I send 1 second of light. Well, that means that this has to be a bigger number, because this quantity right here is less than 1. So this is going to be 1.1 seconds. So if this is true on the spaceship, Einstein says he postulates it here. Just because this person is sitting higher up here and gravity's pointing down here, that the light that they see from here should be shifted. In other words, the amount of time that passes down here is going to be smaller than the amount of time that passes up here. So for many, many years, this was not being able to test it until we came up with atomic clocks. And atomic clocks that work on atomic frequency can actually show that this is a real effect, that his postulate was in fact correct, that general relativity is real, and this effect is known. Now they proved it, general relativity, in 1919, and something that we're going to talk about here in a little while. All right. All right, but to show how this is useful, now I want to get into that example that I told you we were going to do. So let me erase all this. We'll talk about the GPS. All right, GPS. Global positioning system. All right, GPS satellites are in geosynchronous orbit. They're way the heck out there. They're really, really far out there. Several times, I think it's like 10 times Earth radius or something like that. They're pretty far out there. Don't quote me on that. Hamilton would know that number specifically. But the point being is that they can give us accurate information down to fractions of a foot if you get the military grade. And as far as we're concerned, we can get about a meter squared, I think, is what our phones and your standard Garmin's can do. But the point being is that if we're on this planet, okay, here's satellite way out here. This is now much higher from the gravitational field of this. So if this reads a different time, of 10 nanoseconds, that is going to change the position by upwards of 3 meters. And that's just if it reads 10 nanoseconds. Okay, so for every 10 nanoseconds, that gets worse and worse and worse, and all of a sudden, global positioning systems won't work. So let's see whether or not this is even something that we need to do, if this is even important. Okay, there are 2 things that are possibly going to affect this. This satellite is cruising around with a velocity like this, and the Earth is moving as well. Okay, we'll move in that direction, or you could say the satellite's going in the opposite direction, although it's not, because the whole point of GPS is that the satellite stays in the same place above Earth. So these things are moving. This is moving with a much larger velocity than this is. Even though that we're still seeing it, it has a larger velocity. So there's going to be a special relativity effect and a general relativity effect. So we have to use both of them. Okay, so the first one, special relativity. Satellite moving with respect to Earth. And then we have the general relativity effect, where we say that clocks run slower, deeper in gravitational fields. All right, so let's try and tackle the first one, special relativity. Why did I do general relativity first? I don't know. For some reason, I did start writing September general relativity. All right, we're going to need a whole lot of information before we do this. We're going to need to know the radius of orbits, the radius of Earth, all sorts of things. So let's look at GPS satellites. First thing, their orbit. So R of orbit is going to be equal to 2.0 times 10 to the 7th meters. Now, they call it radius of orbit, but what this really is this is the height. This is the distance from the Earth's surface that the satellite is orbiting. And that's going to matter. We'll see why in a second. Okay, the next thing is that the velocity of a GPS is moving at 3.9 times 10 to the 9 meters per second. Okay, now what about the Earth? The Earth has a whole bunch of stuff that we're going to need as well. Put that right here. So radius of Earth is 6.4 times 10 to the 6 meters. Okay, mass of the Earth is 6 times 10 to the 24 kilograms. Useful thing to have in the back of your head. And then we're going to need Newton's gravitational law. So this is 6.67 times 10 to the minus 11 Newton meters squared. I think that's all they use. One other thing, velocity at the equator. The Earth is moving. So if we take the velocity at the equator at the rate that we're rotating, it's about 460 meters per second. Okay, that should give us all the numbers that we need to possibly calculate this. All right, so first thing we want to do over here. Yeah, what do you got?
Like the Earth is not just floating in space, but it's also rotating around the sun.
Yes, and it's possibly another effect. But then again, the rate at which that is happening at a constant velocity
is slow enough that it's.
Yeah, well, it's slow enough, but it's from our reference frame, we're just looking at these two objects. Remember, time dilation and length contraction only happens relative between two different objects. We're saying between these two objects, they're both moving around the sun at the same time. So our reference frame is traveling, so it's not a big deal. That makes sense. All right, so yeah. All right.
This better give us a cool number.
What's again?
This better give us a cool number.
This better give us a cool number? All right, so let's look at the time dilation first. Time dilation for special relativity. Time dilation for special relativity. Now, for that, we go back and we use our equation. The change in t is equal to the change in t naught over gamma v. And this is a good point to mention what I'm looking for or from you guys on your test. I'm going to give you the equations that you need, every equation you need. All I want to know is that you know how to properly use them. Your test is only going to be probably 3 questions long, maybe 4. It's not going to be terribly long. Here's a great example. Here's time dilation. I want to know the time difference that the satellite and the Earth see. Okay? So, which one do I put in here for which one? Is this change in T Earth or is this change in T Earth? And how do you know?
Change it to here would be the one on the right because it's the square reference, right?
Because what?
Like a reference, something working wrong.
No, we're actually not. What if we're down here on Earth? Okay, let's say that we're up there at the satellite and we're watching what the satellite was telling us. Okay, great, that's lovely. Someone who's sat down there and can instantly report back to us. But we're not. What we're doing is we're down here on Earth going, hi, satellite, what do you tell me? And we want to know from the satellite's watch. We want to look at the satellite's watch and see what its watch is changing and then compare it back to here. So in this case, we're looking out to the satellite and the events are happening at the satellite. Does that make sense? And we're comparing it to the relative velocity that the satellite has to Earth. We could do it the other way around and say, I'm standing on a satellite and I want to know You know, down there on Earth, Earth is moving relative to me. What is the time change down there? But, in fact, you get the same answer, just do the inverse of it. This won't always be the case, but in this case, you'll just get the inverse. But we're down here at Earth wanting to know the change in satellites. So in other words, this has to be the satellite up here. So we're changing to the Earth is equal to changing to the satellite.
So is that because, I think you said one time, like, the delta T is the one that's not moving.
The delta T is the, no, the easiest way to think about it is which one is the delta T naught. The delta T naught is the location of the events that you're interested in. So in other words, if you're Bob and you want to ask about what Anna's watch is doing in between two different times, Anna's watch is the watch you're looking at, that has to be the delta T naught. So it's the watch that you're looking at, it's the events that you're looking at. We're looking at the satellite's watch.
We're looking at satellite now.
Okay. So, this being said, our gamma V, of course, would be over square root of 1 minus V squared over C squared. Okay, now our velocity term in here. Now, technically, we should do the difference in the velocities that we're moving, this guy relative to this guy. But seeing as how we're moving at 3.9 times 10 to the third meters per second, and Earth's only moving at 460 meters per second, this is inconsequential. Okay. So you can run the numbers with this, it's just not going to make any difference, really. So we put in the velocity of the satellite relative to the Earth and where it's moving into here. Okay, off it goes, and then we're going to get our gamma V, and then we take a change of time satellite to change of time Earth. And we are going to find that change in T Earth one plus 8.5 times 10 to the minus 11th, change it to the satellite. Okay, so in other words, from our Earth point of view, our Earth time, if I'm looking down here and I'm saying that 1 year has passed, okay, what would the satellite say, more or less? More. Nope, less, because this number is greater than 1. This is plus. So this has to be less than 1 year. So, the fact that that's less than 1 year, what does that mean? Okay, so we're down here and we're watching this object that's moving very, very quickly. We're saying that less time has passed. That makes sense. This gets back to the whole special relativity says that if Jared and I are moving apart from each other, I see Jared aging slower, he sees me aging slower. We're both thinking that less time passed from when we're looking at that. That's what it looks like anyways. So the same thing is true. If you went from the satellite's point of view looking down at Earth, you find the same thing. Okay, so now let's go on to general relativity. General relativity is going to tell us that our change in T lower is going to be equal to the change in T higher times the quantity 1 minus GH over C squared. Okay, there's a problem with that equation though. When we write this, what we really should write this as is the minus the change in GH. And this isn't directly in your book. They more or less just kind of pretend it's there. The change in GH. Because when we were solving this before, we were assuming that gravity was the same in both cases, and we assumed that the height difference was the same in both cases. But if we're going to talk about a difference in these, we need to know the change in G and the change in H, because they're both going to be changing for this system. So it's a slight problem. All right, so if we rewrite this out, I could say change in T lower is going to be equal to change in T higher times 1 minus C squared times G mass Earth, radius of Earth squared, times the radius of Earth. Okay, this is my G value right here. And you guys remember back in 2211 how we calculated G using this? Or you guys doing Hamilton's? I'm sure you guys do that.
Yeah.
So in that way, this is my H value, my capital H. Why is that my capital H? Because I'm saying that's the radius of the Earth. That's where I'm starting. I'm right here. Okay, this is my height from the radius of the Earth. The reason being is I need a change in height. So in a second here, I'm going to have G ME over RE plus H squared times RE plus H. Essentially, boom out.
No, I'm fine.
Oh, you guys look concerned.
Well, I'm concerned about this.
Okay, let me explain. This RE plus H, we're subtracting these, all right, such that the distance that we're going to be higher up here, this RE plus H, the distance away is going to be just this H right here.
Right.
This works out to be our H. It's the difference between these two factors that is my GH over C squared.
Why did it become a lowercase h?
Okay, when I say RE plus H, what I'm referring to lowercase h as is this distance right here.
Okay.
So capital H is the general form of the equation. Little h is my specific h for this problem. I just didn't want to necessarily confuse. So, and if you guys remember, this is how we calculated a change in gravity when we went down to high altitudes. Okay, you have to add the h in here the farther away you are from Earth, because gravity is going to get weaker. So, this cancels with this, and this cancels with this. And we get GME over RE over all of that. Okay, so this becomes this is supposed to be 1 over c squared here, I missed that when I pulled it out. So we've got G ME over RE minus G ME over RE plus H. Simplifies. Now, what are we going to put in for all these numbers? The mass of the Earth doesn't change, the radius of the Earth doesn't change. What is this RE plus H? Well, here's the radius of the Earth right here. The H value is actually this R orbit, because that's the distance from Earth that we're orbiting. So in other words, RE plus H is going to be 2.64 times 10 to the 7th. This is times 10 to the 6th, or I can write it as 0.64 times 10 to the 7th. Let's go ahead and write that as 0.64 times 10 to the 7th. So we add these two together, we get 2.64 times 10 to the 7th. That's the number we're going to throw in the down here.
Okay, what number goes down there?
What?
What number goes down there?
2.64 times 10 to the 7th. I'm kind of running out of room here on the board. So
No, the second one above that, all of those terms just cancel out.
this term, no, it cancels with one. They're
Yeah.
squared in the bottom. So this cancels with the square. That's why we ended up with it. So this is how we calculate our G normally, and this is our H left over. All right, so what do we get for an answer for this when we throw all those numbers in? Okay, so we're going to find that change in T lower. I'm really filling up the board today. And I can change this to change in T Earth. Let's write it as Earth. Let's change in T satellite. Okay, is there two L's in satellite or one?
We're at one.
I have two.
I like one.
Occasionally I have one, occasionally I have two.
I think it's one.
I think it's
I
one?
feel like two is right.
It's two.
That is good.
Someone's voting.
I'll go back and add. There we go. How many in the book?
Two.
Two. All right.
Look,
Two's
look,
the answer.
they don't know.
All right. Change in T satellite is equal to, what do we end up with here? We get an answer of 1 minus 4.4 times 10 to the negative 10. Okay. So this is to say that if 1 year passes here for the satellite, on Earth, according to the satellite, this is going to be greater than 1 year. So special relativity and general relativity actually have opposite effects on this. And these are real effects that are going on. Okay? So they, unfortunately, they don't quite cancel. General relativity actually is a larger effect. All right, so I'm going to leave that up, and I'm going to go erase this stuff over here.
Remember when we measure the difference now?
Yep. We did just measure the difference. Now we just got to put some numbers in it to make it a little bit more interesting. So if we add these together, we're going to say our time dilation total time dilation total is going to. Oh, I lied to you guys. I gave you the wrong number over there. I jumped ahead.
Or look at the pen.
Oh, I'm sorry. 1 minus 5.26. This is your third class with me, David. You should know better.
Times 10 to the
You should
negative
know
10th or
Negative 10. Yeah, no, jeez. It has to be a number that's positive, so that wouldn't work out too well.
Wait, it's in the morning.
Okay. So minus 10. The point being is that the total time dilation, what we do is we add this number, the 5.26 times 10 to the minus 10, plus the 8.5 times 10 to the minus 11, which can be written as 0.85 times 10 to the 10. And we get our total time dilation is a function change in t Earth is equal to change in t satellite. With two L's this time, they're crossing apparently. 1 minus 4.4 times 10 to the minus 10.
Now, that's still in general relativity or special?
Both. That is total time dilation. What I did was I just added this term. I literally just added this plus this.
All right.
The general relativistic term is dominant. The special relativity one actually cancels it a little bit. So, we started off with this problem by saying 10 nanoseconds is going to affect the GPS satellites by 3 meters. Okay, so that would be the soonest that we'd be in some serious trouble. So let's figure out how long that would be. We need a difference of 10 nanoseconds now, okay, which is slightly difficult to do. So let's multiply this through. Okay, I'm going to write this as change in TE is equal to change in TS times X. Because I got to do some algebra here, and I really don't. Oh, I'm sorry. 1 minus X. 1 minus X. I got to do some algebra here. It's going to be much quicker if I can draw it that way. Okay, so we can multiply that out. Change in TE is equal to change in TS minus change in TS times X. I can now subtract it on this side. Change in TE minus change in TS is equal to a negative change in TS X. Okay, this right here is what we're looking for. The difference between those two. That's where we can put our 10 nanoseconds in. Okay. So now what we can do is I can divide this by X. And I'm going to find my change in time in the satellite. What the heck did I just do? Okay. This is my 10 nanoseconds. The change in time between these two is 10 nanoseconds. If I divide by my factor x, this negative 4.4, we'll figure out how long in time do we have to go by, how long is total time gone by on the satellite, in order for this to have seen a difference of 10 nanoseconds here. Does that make sense? So what we end up doing is we take 10 nanoseconds divided by 4.4 times 10 to the minus 10, and we get an answer equal to 23 seconds. This happens quickly. In 23 seconds, the two clocks are already off by 10 nanoseconds. The GPS can no longer read where we are on Earth, not accurate to 3 meters. In another 23 seconds, it's off by another 3 meters. And this just keeps getting worse and worse and worse unless this can be accounted for. So this is where I said that it was going to make you guys way more employable. Without understanding totally special relativity and general relativity, our geosynchronous orbits would not work. We would not be able to have time synchronization between the two. We have to account for these things, which I think is pretty cool. And you can actually get employed to work on this sort of stuff. So let's say you want to change to a different orbit other than geosynchronous. You want to be in a low Earth orbit. You still have to calculate how far these things are off. Now, what affected these calculations? Things that you have to adjust. All right, let's go back and look at that. Let's look at general relativity. General relativity is a function of gravity and the height. Okay, so g, mass of the Earth, the radius of the Earth, none of that's changing. The only thing that possibly changes in here is h, this little h. How far away are you that you're orbiting? In other words, how far away are you from the gravitational field? That's all that changes. That's the only factor that you need to know. So you can literally, and they have them, computer programs that just write, all right, what is your height above Earth? I will tell you how much your general relativity is going to affect your time. So nice and easy. Special relativity. Go over here and look at special relativity. We see that, okay, we've got our time dilation. Time dilation is just a function of the velocity difference between the two of them. Now, if something is in geosynchronous orbit, we know exactly what, I've already raised it, we know exactly the speed that it's going, 3 point something or other. Do I have that written down? I don't. 3.8 times 10 to the third, 3.5 times 10 to the third meters per second. It is really cruising out there, and it has to in order for it to stay in line around the Earth. So if I'm Earth and the satellite's out here, I'm just rotating like this. You can see that the satellite's obviously moving at a lot quicker speed. But it's a known speed. So we can plug that into it and figure out what the special relativity is as well. Nobody wants to see me spinning around.
They just completely missed that.
I know, that's okay. That's okay.
So in 1 year, the satellite is off by almost 800 miles.
There you go. So not a very useful global positioning system. So for every single orbit, you need to know your speed to affect time dilation and special relativity, and you need to know your height above Earth to affect what is actually going on for general relativity. From this, you can recalculate your satellites and actually know accurate times on both. Okay. Questions on this problem before I guess and erase all of it? Kyle, you gonna make it?
Maybe.
Really?
You win. Go answer.
Yeah, I think cool answer. I think this is really kind of neat stuff. And it's real. Now, we can detect this using atomic clocks now, but back then, this was all hypothetical. Einstein's just spewing this crap out of paper, and nobody had any idea how to test it. So the next topic we're going to talk about is, how did they figure out how to test this? Einstein became very famous in 1919. Before that, he was just a crazy idea that kept coming up with stuff. We keep talking about this 1905 where he put all this stuff out. Nobody believed him. It didn't matter. I mean, now we're retrospectively go back and say that was pretty cool. 1919, he instantly became extremely famous. And all of this stuff, the E equals mc squared, general relativity, special relativity, he all did right around the same time. I mean, it was a pretty short amount of time to put all of these puzzle pieces together.
Maybe it was aliens.
What'd you say?
Maybe it was aliens.
Maybe it was aliens. Maybe Einstein was aliens. Okay, so the whole point of this is that this discovery is that gravitational fields warp time. It's a fact. We can actually prove that. Like I said, with the atomic clocks, we can pass them around and we can up and down and show that time has actually changed. So a relative velocity between the two objects also warps time. So then the question becomes, well, we say gravity warps time. Usually the phrase is generally heard, gravity warps space-time. And it's true, just like we saw that the length contractions and time dilation are the same. If we had more time, we could go through examples and show that gravity can also warp space. So there's a really neat picture. What do you got, Drew?
I was going to ask about the space.
Go ahead. What do you got?
No, I was just going to ask, so that also.
It warps space. It necessarily has to be able to warp space. So, and it's really difficult to obviously describe this, but there's a neat picture at the bottom of page 49 that talks about warp space-time. A heavenly body, an object that has a large amount of mass, will change the way space and time move around it. Okay. Now, a couple other things that this told us. So, gravity warps space-time. Okay. But what we were just showing, we were talking about a flash of light that went up, and it was redshifted from somebody that was just further up in a gravitational field. Now, when we were doing all that, we never even considered the fact that the Earth was rotating. Remember, we only did the fact that the Earth was rotating when we were curious about the velocity difference between for special relativity. That's the only part we cared about. So even if we had a giant hunk of Earth that wasn't even moving, just being farther away from the Earth, we would see the light being redshifted. So that is telling us that gravity affects light. This is even a bigger deal. Gravity affects light. Now you guys might have heard of things like black holes where light can't escape. Now that's the type of thing that we're trying to talk about right now and understand why that's the case. It's a problem because as far as we know, light doesn't have mass. There's actually some arguments that says that maybe light does have mass. It's just so small we can't tell. But for all intents and purposes, we can determine light has no mass. So what was Newton's law of gravity? Remember off the top of your head? We had most all of it over there still.
Was there an M there?
There's an
And a G.
and a G and
And a
G mass 1 mass 2 over r squared.
okay.
Newton's law of gravity, in fact, every one of Newton's laws turned out to not be so much of a law, just kind of a special case. This is another one. So we've got Newton's law of gravity here that says gravity affects things with mass, but we're saying that gravity affects light. How does this happen? Turns out that this is a special case. It's a special case in two ways, not even just one. Just like all of other Newton's laws were special cases for low velocities. This is a special case for low masses, for even small masses. And what we're going to find out here in just a few minutes is that even for masses that get as large as the sun, this equation doesn't work anymore. Okay? And the other thing is it doesn't work for masses when they get so small or non-existent. For example, light. So this only works for, normal Earth-sized objects, anything from us to Earth size. If anything gets too small, such as a photon, or gets too big for the sun, and this equation no longer works. These are one of the things that we don't have a whole lot of. We don't have what I would say, a final version of this equation that we fully trust. Gravitational law still escapes us to some extent. All right. All right, and one of the ways that we wanted to see this, and one of the ways you can see this, is deflection of light by the sun. So that brings us to the next topic. Deflection of light by the sun. What do I mean by that? All right, let's go back to our spacecraft. So let's say we're hanging out in our spacecraft and we're accelerating up. A is equal to G, and we have a light source that goes off, shoots that way, and is going to fire to the right in our spacecraft. This is us. We're happy in our spacecraft. Okay. Short time later, and boy do I mean short, because this is a light beam. It's kind of going to cross from one side to the other pretty darn quickly. If we are accelerating, and light was sent straight across, this is just like a projectile motion problem, then in a little while, the light is going to be farther down. We're going to see it down here. So it had started up here, and is now down here, because our frame of reference went up, even though the light was shot straight across. Okay, next one. If that's the case, we have now moved even farther, such that now light is going to be like this. Now, why is it not just a straight line downward? Because we're in accelerated motion, not constant velocity. If this was just in constant velocity mode, we would just see the light go at an angle like this, because it was shot straight across, but we were moving upwards. Okay? I'm trying to think of a good example of that. Yep, can't think of one. But since we're accelerated, this is going to keep moving farther and further. Again, we get back to Einstein's postulate, and we say, okay, dude up here on this wire, you can have legs and tail, why not? That says that light would have to bend towards a gravitational field. And the question was, is this actually true? Well, if you do measurements based on the mass of the sun turns out to be really small. The deflection of light is only 2 parts per million on the sun. So what the heck are we going to do? Plus, there's another part about this. If we want deflection of light by the sun, it can't be light from the sun. That doesn't work. It has to be light from another planet. Kind of a problem. Okay, look at a sun and then look right next to it and look at a planet, or look at another star behind it and just tell me what that light looks like. How? Obviously, the sun is going to block out any light from any other source. It's going to be nearly impossible to determine any light. So the whole idea, what we need to determine this is we're here, we're Earth. Here's the sun. We need some distant star that's way far away to shine light that is supposed to come right here towards the sun. So in other words, we're rotating. We're watching when the sun's over here, and relatively we're watching here. We know where that star is. Okay, we know exactly where that star is because it hasn't moved. When this light gets to right here, what we want to see is what happens is it's going to go like this. Is it going to actually bow towards the sun? And that's what we're saying that the gravitational field should suggest that it necessarily does. So there was no way to do this until 1919. A physicist, which they don't even mention who, and I don't remember his name either, came up with the idea of, well, let's just wait till a solar eclipse. So what ended up happening was they waited to the point that the moon was perfectly in the way. I don't know why they are so small. We'll work on it. It works for this. The moon got in the way such that the sun was mostly blocked out. Okay, so then we can see light that's coming from a source, and all of a sudden, if the light would look like it would change. And you're like, well, wait a minute. A couple of things to think about on this. You're like, wait, light that we're seeing from the star is billions of years old and blah, 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 because it's so far away. So how is it changing? We're not looking for the light that is instantly coming from the star. We're looking from the light that had been traveling, marching on its way here for billions of years, and just got to the sun and then bent. In other words, light, I think, takes, what is it, 7 minutes or something like that to get from the sun to here? About that. So we only had to wait 7 minutes. We didn't have to wait that long to see the deflection. And you see all of a sudden it looked like the star went, whoa, that was neat. How'd the star do that? And that's exactly what they were able to show. So even with the instrumentation back in 1919, during the solar eclipse, watching this, watching the stars near the sun, and it'd be the equivalent of you're staring up there at the sun and you've got all these stars and they all look like they pulled towards the sun all of a sudden. That's exactly what it looks like because the light itself bent towards the thing with large mass. And they were able to measure this, I think it was, what, 2 arc seconds? And they were able to get to it. But in either case, they had predicted exactly what it should have been based on Einstein's theory of general relativity, and they proved it. And then so Einstein became instantly famous. General relativity is real. And later, of course, they started proving that special relativity and everything else was real. That was the first time they could really put an experiment to it. What do you got?
Is this that thing where they had a bunch of observers all over the world, like measuring things at the same time?
I'm pretty sure that there's more than one, yes, more than one group that was doing this, because this was a big deal back then. I mean, basically, at the turn of the century, 1900, everyone says, physics is done, Newton did everything. And then there was just a couple little things that weren't working out, and then Einstein says, you are all wrong, and here's all of this math that goes along with Maxwell equations that says special relativity, general relativity, rest energy. Energy is equivalent to mass, and you can change one to the other. It says, oh, by the way, here you go. And then so we just waited around to prove this stuff. So when that time came around, there were a lot of people that were invested. Because there's a lot of people that didn't like Einstein's theories. And we said, no, I don't think so. I want my ether, and I want my Newton's equations, and they were really against these ideas. And they had other ideas that, light had mass and things like this. And he showed that that isn't necessarily the case. So yeah, and he became really, really famous. Okay. Now, next thing I want to talk about is the precession of Mercury. This was another clue of general relativity, and actually was the way that they started expanding that equation over there. Precession. Now, let's have a star. Ta-da! That's our sun. Our sun is there. All the planets go around the sun. At different points, they're closer to the sun than others. So we get summer at certain points. It's nice. So your planets are going to orbit the sun like this. Okay? At certain points, you're going to be closer than others. Now what happens is, if there was nothing else in the universe, you would stay in this loop forever. And you would just go like this, around and around and around. And you come around, and then you would slow down over here, and then you speed up and whip around, and slow down and whip around as you're going around. Because the forces are stronger, so you're going to have a tighter radius. Not a tighter radius, but a tighter term. Okay, what happens is, there's 8,000 other planets that are going along. Okay, so what ends up happening is they actually shift you from this path, such that sometimes you're right there, sometimes you're right here, and around you go. So in other words, when all the planets are lined up like this, their bodies are affecting you, and you're ever so slightly going to be pulled in this direction. Now, these circles are obviously an extreme example, because out here we freeze and here we burn to death. Here we're talking very slight changes in this. So Newton, when he became famous for coming up with his equations to map all the celestial bodies, everything he did, he got right. He got all of the other bodies right, he figured out everything, except for one thing, Mercury. Mercury being the closest to the sun. Its pattern here did not match anything that they came up with. And for the life of them, they couldn't figure out why. Well, it turns out it's a general relativity effect. Back here when I said that this is only a special case. This is a special case for small masses and relatively large distances. Now when you get Mercury close to the sun of a giant mass, it turns out that that equation is incomplete, and the mass of the sun was actually warping space-time. So if we look at this from the plane of the sun, now I'm trying to do essentially a one-dimensional picture of a four-dimensional project. Gotta go?
I would mean it inhibits the path.
Okay.
I'll be there for the rest of
No, we're just about that anyways. You missed the test that was on Thursday, this coming Thursday, and then now it's been moved to Tuesday. I wanted to have a test on Tuesday, but they bullied me out.
Well, you wouldn't be here anyway, would you, Greg?
Wait, what?
This Thursday, you're not gonna be here?
No, I'll be here this summer.
Okay.
But it's Tuesday.
Tuesday we have a test. Is there any way we can talk to Weaver and get you out in time?
I can just leave.
Well, actually, don't worry about that, because I can just bring you up to my office for the last half hour. As long as
It's not a problem.
oh boy, okay. Test on Tuesday.
Alright,
Your homework's due on Thursday.
I'll talk to you later.
Sounds good. All right, so we've got the sun down here. So the sun, what the sun is doing is it's bending space-time like this. Now, for every single other planet that's out here, it wasn't affecting anything. The only one that it was affecting was Mercury, because Mercury is right on the edge of this space-time.
What's this line thing?
What's this line thing? Yeah, it's the equivalent of the diagram that you have at the bottom of 49. If you go to page 49. It's talking about warping space-time. And it's the same idea. There's another picture, if you go to the next page, the same thing I was talking about before, on page 51, that talks about how light is bent towards it. It's a graphical interpretation of general relativity that shows that if there's the dip in the field, when light comes by something, it's going to kind of dip into it like that as it goes towards you. So the same thing was true with Mercury, and then when they were able to expand this equation, which I don't think happens in this book till like chapter 13 or something like that, they're able to then prove that yes, and they very accurately depict what Mercury's precession was. So just more proof that general relativity is real. It's not just a formula that we came up with. GPS satellites being the one that we need the most, though, or see the most. Okay, we're actually done early today, because that's all I have for this. And I think we're ready for the test.